This is a brief lecture about the polarity of molecules. We've talked in the past about polarity of a particular bond, but now we're going to talk about the polarity of an entire molecule. In order for a molecule to be polar overall, it must first of all have polar bonds. So if the entire molecule is made up of nonpolar bonds, so a bunch of chlorines all hooked together, for example, or carbon-hydrogen bonds are nonpolar. So if the entire molecule is made up of carbon and hydrogen only, that's nonpolar, and you don't have to go any farther. But if there are polar bonds, there is one more step that you need to use to evaluate the molecule to determine if it's polar overall. The molecule must have an unsymmetrical shape, at least with respect to one plane, in order to be polar. So just because a molecule has polar bonds doesn't mean the molecule as a whole will be polar. Carbon dioxide is a really good example. The carbon-oxygen bond is quite polar. You can draw the partial negative by the oxygen and partial positive by the carbon. But it so turns out, because there is perfect symmetry in this molecule, that the two partial negative poles completely cancel each other out, and so overall it is a nonpolar molecule. Why is it important to know whether or not a molecule is polar? That's because that affects a lot of the molecule's properties, and that's because the polarity of a molecule determines what type of intermolecular attraction it will experience with other molecules. And so if you have molecules A and B, and they are both polar, they will experience stronger attraction to each other. That's called between molecules attraction. And that affects all sorts of properties like boiling points, melting points, how well it dissolves in water. And as you're learning throughout this lecture to determine whether or not a molecule is polar, keep a lookout for non-bonding pairs of electrons. Those, more than anything else, determine whether or not a molecule is polar. And so I already talked about carbon dioxide having polar bonds. Remember that if we say something has a dipole, it simply means it's polar. What we say is that the dipoles of carbon dioxide completely cancel each other out, and that's because it is symmetric right down the middle of the carbon atom. And what that means is that if you imagine this line I've drawn as a mirror, the mirror looks the same on both sides, and therefore that gives it symmetry, and overall it is nonpolar. Looking at water, for example, if you didn't know the shape of water, if you didn't know how to draw Lewis structures, and you thought it was linear, you might think that water was nonpolar too. But because you know how to draw Lewis structures, and you know that there are actually two non-bonding pairs of electrons on the oxygen, and that it happens to have an electron domain geometry of tetrahedral, you know that the molecular geometry is bent. Okay, it's not linear, and therefore, although if you draw a line straight up and down, it's symmetrical across this plane, if we draw a plane this way, it's not symmetrical on top and bottom. Okay, so it's got to be symmetric in all planes. And that'll be the case anytime a central atom has non-bonding pairs of electrons. It will be not symmetric. And so if you look at the partial charges that would be put on water, obviously the partial negative charge would be over the more electronegative atom, but also wherever the non-bonding electrons are located on that atom. And so if you remember how to draw a dipole, you put the arrow pointing towards the more electronegative atom. So we would draw a dipole like that for water, showing that the more electronegative end is where the arrow is pointing. All right, so the steps, if you're the type of person that likes to write down steps for predicting polarity, First thing you do is draw the Lewis structure so that you know the molecular geometry. That's critical to be able to do that. Then ask yourself whether the actual bonds in the molecule are polar. If all of the bonds are nonpolar, it's a nonpolar molecule. You don't have to do shape or symmetry. If there are polar bonds, then you have to determine whether the molecule is symmetric. And just to explain a little bit more detail why molecular polarity is important, it affects big time whether or not a molecule is soluble in water or other solvents. And water is a polar molecule, which we just discussed. Therefore, other polar molecules dissolve well in water. I think I've told you this before, but it's another chapter that's good to remember it, that like dissolves like. That means polar solutes will dissolve in other polar solvents, and nonpolar solutes will dissolve in nonpolar solvents. Well, ionic compounds are extremely polar. Remember what polar means. It means there is some formation of charge, whether it be partial charge or whole charge. And so ionic compounds are extremely polar, and they dissolve, most of them, very well in water. Molecular polarity also explains why oil and water don't mix. Oil is a long chain hydrocarbon, which means just a bunch of carbons bonded together with hydrogens hanging off the side. Okay. And on and on and on. So doesn't matter if it's symmetric or not, very nonpolar simply because it has carbon-hydrogen bonds, and that's it. Water, of course, we know is polar, and so those two do not mix well together. So here's a test for yourself to see if you're able to determine whether polar or not. So I think it's really important that you turn off my lecture. I present the answers on the next slide, but you go through the process yourself. Make sure you can do it, and this will be part of what's on your quiz on Tuesday. So remember to draw the Lewis structure first, and then determine whether or not the molecule is symmetric. All right, so here are the answers. I'm hoping you did it yourself. There are no pure hydrocarbons, no molecules that only have carbon and hydrogen are all the same atoms. So there are none that we can say right off the top have only nonpolar bonds. And so we'll start with NH3. And if you were to draw the correct Lewis structure, I don't have the non-bonding pair here, so there they go. If you draw the Lewis structure, you notice that its molecular geometry is trigonal pyramidal, and that it is not symmetric. Remember I said anytime there's a non-bonding pair on the central atom, it won't be symmetric. And so if I asked you to draw a dipole for this, remember the arrow points toward the more electronegative end. Okay, so that would be its dipole. Water, we already know, is polar and not symmetric, so I'm not going to beat that into the ground. CH3Cl, okay? That is polar. It has a tetrahedral molecular shape and no dipoles to cancel out. Its overall dipole points toward the more electronegative chlorine. CH2Cl2 might be a little bit trickier for you, because if you were to draw one line of symmetry like that, it would look polar. But remember, you have to be able to, it has to be symmetric through all lines of symmetry. But if you draw a line of symmetry this way to separate these two atoms from these two, all four atoms in a tetrahedral are equivalent. So even though on this two-dimensional drawing they don't look like it, they're all equally spaced from each other. So, but if you look at this line, they certainly are not mirror images. So that is not symmetric, and it therefore is polar. And of course the dipole points in the direction of the chlorine, the more electronegative chlorines. And finally, xenon tetrafluoride. Okay. And it turns out that its shape is square planar. Its molecular shape is square planar. It starts out as an octahedral electron domain shape, but because of the non-bonding pairs, it ends up square planar. And because all four of the atoms bonded to the xenon are identical, so if you were to draw the dipole for each bond, they would exactly cancel each other out. Okay? So regardless of where you draw your plane of symmetry, whether it's straight up and down, it's a mirror image, or whether it's straight down the middle, that's also a mirror image. So that is nonpolar. That's it for polarity.